Good morning to all. Today I have come up with a new topic in theory of structure subject, which is known as dams. Actually, dams and retaining walls is a single chapter, but in recent curriculum they have separated it out as dams as second chapter and retaining walls as third chapter. So now I'll go into the topic. So what are the basic objectives which we achieve after this tutorial are upon the completion of this class, you would be able to define a dam. I mean to say, what is a dam actually? There's a lot of confusion for so many people between dam, reservoir, and some other barrage and some other structures. So initially we'll define a dam. And secondly, we need to identify the forces acting on a dam. What are the main forces which are acting on a dam while analyzing a dam? And the third part is the most important part, analyze the dam under the action of forces. So analyze the dam under the action of forces means it includes mainly of calculation of different forces which are acting on a dam. So these things we'll cover in this tutorial. So if you go into the subject, so initially what is meant by a dam? Dam is a structure constructed in masonry or concrete across a river or a stream. So, a dam is a structure constructed in masonry or concrete across a river or a stream. So, there is a separate theory and separate concepts which involves what is the site selection for a dam structure. So, that means at which location we need to take up the construction of a dam. So such points will be involved in that. So to store a large amount of water for drinking, irrigation, power generation, and etc. So what is the usage of dam mainly? Generally, it will be constructed for diversion of water actually. So diversion of water, nothing but either you can use such water for drinking purpose or most importantly for irrigation purpose. I mean to say by constructing some canals on the upstream side of a dam structure, and also for hydroelectric power plants, that is for power generation purpose. So these are the main things or significance of a dam for which we need to construct it across a river or a stream. So in general, a dam is constructed for these two purposes, actually for drinking and irrigation, and if the capacity is more, it can be used for power generation also, right? So if you go into the next topic, which is forces acting on a dam. The following forces generally act on a dam, that is self-weight of dam represented by capital W. Self-weight of dam nothing but it can be a masonry or concrete dam. And second one is pressure of retained water represented by P. So pressure of retained water. So here we can see the cross section of a dam. We call this side as upstream side of the dam and this side as downstream side of the dam. So this is a typical trapezoidal cross section of a dam. As we can see, top side we have certain top width and the bottom side we have certain different bottom width. So these are the assumed dimensions of a dam. Top side we have considered as small a and bottom is small b, and on upstream side we have a height of water up to small h, and we are considering capital H as height of dam. So as I have mentioned earlier, what are the basic forces which are acting on a dam are self weight, nothing but weight of the dam, capital W, and water pressure from the upstream side. So water pressure from retained water, that will be P, right? Or that will be in the horizontal direction, and as we already know that weight will be acting perpendicularly to the ground surface, that is capital W. So generally P and W will be acting on the dam. Because of these two forces, as they are orthogonal, there will be a resultant force which is coming out of these two forces. We'll call it as capital R. So now totally there are three basic forces which are acting on a dam, that is horizontal force P due to water pressure, self weight of the dam, capital W, and resultant force, capital R. So like this we can mention the basic forces which are acting on a dam. So here, while analyzing or while calculating certain forces, we need to keep one point in our mind. That is, note, for analysis, we consider unit length of the dam. So this is the important point. If you forget this point while derivations or while analyzing the dam structure, you might get confused while writing the equations. So whatever it may be the length of the dam, if you consider while analyzing as 1 meter, the length of the dam is 10, or I mean to say 10 meters. For an example, for 50 meters, if you simply multiply that value into 50 meters, we will get the ultimate forces or self weight. Right? So this is the important point. This is similar to like while calculating the loads on a slab for a unit width, right? In RCC subject. So in the similar way, we'll consider as a unit length of the dam while analyzing. So forces acting on a dam are horizontal pressure, water pressure P, weight of the dam, and resultant force. So analysis of a dam. This is the important part of this tutorial. So what is meant by analysis of a dam? So it involves calculation of magnitude of W. I mean to say calculation of self weight of the dam and the distance of its line, of action from vertical face of the dam. So this will see here calculation of capital W and the distance of line of action of force, that is this one, line of action of self weight to the vertical face of the dam, that means here X. So this and W, these two we need to calculate initially. And the next is magnitude of P and the distance of its line of action from bottom face of the dam. So here magnitude of P, generally it will be occurring here. If you project it here, it will be here. So capital P and vertical distance from bottom face of the dam. Right? If you consider this as small y. So we need to calculate P and the distance of line of action, that is this line of action, and line of action from bottom face, that is y. The combined effect of W and P, the resulting stresses at the bottom of dam. So after calculating W and P, the final part is the combined effect of W and P, that is combined effect will be resultant, right? And the resulting stresses at the bottom of dam. So this we'll do in the next class, that is sigma values, stresses maximum and minimum. These two values we need to calculate. Resulting stresses means maximum shear stress, maximum stress and minimum stress at the bottom of the dam because of W and P, that is nothing but resultant. So these three things, this one and this one and this one, involves analysis of dam. So if we solve these things, it means we have analyzed a dam structure, and further we can check whether the dam is safe or not by calculating factor of safety or resisting moments and overturning moments, etc. So but for all those things, this is the basic knowledge, right? So if you go into if you go into the next part, that is calculation of these forces. So calculation of forces, in that first one is self weight. So self weight, how we need to calculate the self weight of the dam. So where is on this? So self weight, we are denoting it by capital W. So you already know that specific weight here is considering as rho equals to weight by volume, right? So here we need to get weight. So weight is equals to specific weight into volume, right? And volume area into length. As I have already told you, length we are considering as unit length, and area of trapezoid is area here top width plus bottom width by 2 into height of the trapezoid, right? So here area we got it as a plus b by 2 into h into 1 by 2, right, into rho. So that is what I have written here, a plus b into h into rho by 2, right? So in this way we can write the equation for a self weight of the dam. So where rho is the specific weight of the masonry or concrete, which I mean to say dam material. It should be like whatever the dam material is there, that dam material self weight we need to substitute in place of rho. So by this we got W value. As I have mentioned, we need to calculate magnitude of W and then the distance of line of action from the vertical face of the dam. So it acts through the centroid, right? There is a basic thing, that is common sense. So self weight acts through the centroid of the dam structure. From that point to vertical face, that distance we need to calculate now. So it acts at a distance of x from vertical face, that is heel. Here call this part as heel, this part as toe. Just like our feet, front part is known as toe and the rear part is known as heel. So from here to here we need to calculate the distance. So from the knowledge of centroid we can write this equation. In engineering mechanics subject, in centroid chapter, you will be knowing these things, right? So how we need to calculate the centroid of a trapezoid, centroid of a rectangle, triangle, and various other shapes. So by using such knowledge, we can write the centroid equation as a square plus ab plus b square by 3 times of a plus b, right? So we have a and b values here, and if you substitute those values, you can get the x value. So in this, first part is completed. The second part is magnitude of P, that is calculation of forces in the dam, that is because of horizontal force. We need to calculate now horizontal force. So horizontal force P is because of due to retained water on the upstream side, right? So that I have mentioned here, it is due to water pressure. So from hydraulics, we know that water pressure varies from 0 to WH. I mean to say from 0 to, this is WH, right? 0 at the water surface and WH will be at the bottom of the dam. So the variation will be linear, and this thing you will be learning in your hydraulics. So as a material is water, I mean to say the liquid is water, we can use specific weight of water as 10 kilonewton per meter cube. And also, if you just remind your basics, it acts at a height of h by 3 from bottom. It means the centroid. When h by 3 from the base of the triangle means it's a centroid distance, right? So the P acts at a centroid which is at a distance of h by 3 from bottom. So h by 3 from bottom. And if we take, now if we calculate the area of the triangle shown, we'll get as this is a pressure distribution diagram, this is the pressure distribution diagram, this one. So if we calculate the area, half into omega h into, and it is a WH into height, base into height, h, which is equals to half into WH square. This is pressure. The area is known as pressure because it is a pressure distribution diagram. So by this relation, we get horizontal water pressure as half into W into H square, right? Now we got W and its distance x, P and its distance is h by 3, right? These two things we have calculated now. So after this, we need to calculate the combined effect of W and P. That is nothing but combined effect of self weight and horizontal water pressure. As I have already mentioned, because of these two forces, there will be a third force which is known as resultant force, right? So that resultant will be capital R, and capital R is equal to double D square under root of double D square plus R square, because these are acting at a 90 degrees, and the resultant will be obviously at an angle of 45. So if we apply Pythagoras theorem, we get R equals to under root W square plus P square in magnitude. This is because only, or I mean to say, this condition is applicable only for the vertical face of the dam structure. Only if the upstream side is as having vertical face, I mean to say of 90 degrees, then only such relations are possible. If it is having something of an inclination like this, then the whole thing, this R value and everything will get different values than compared to this. So that is why before analyzing a dam, you need to observe whether its upstream face is vertical or not, or it is at an angle, right? So this thing you have to remember, you need to follow, or else everything will go wrong. And now this R is projecting out at an angle of 45 degrees from P and W. This will cut the bottom width of the dam at some particular point, say C. So R is having a certain line of action of force. So that line of action of force of resultant strikes at a distance of small z from heel, that is from vertical face of the dam. So we are giving a name for this distance as z from the vertical face of the dam. So this z will be having a predominant role on the stability of the dam structure, that we will be discussing in future tutorials, how it will play a major role and all. So we need to calculate this z as well. So if you observe the things nicely, we are calculating a force and its acting distance. Right? In the second thing also, we are calculating a force and its acting distance. And in the third case as also, we are calculating the resultant and its acting distance. So why we need to calculate the force and its acting distance means, ultimately we'll calculate the moments, right? So moment will be moment is equals to force into perpendicular distance, right? So as I have mentioned earlier in this tutorial, ultimately we need to check whether the dam structure is safe or not. For that we need to calculate factor of safety, which will be equals to resisting moment by overturning moment. So resisting moment by overturning moment means if the factor of safety is greater than 1, dam is safe. So these all conditions we'll see in the next tutorials. So the thought of explaining all this to you now itself means why we need to calculate the force and its acting distances and all that I want to make it clear to you. So we are calculating the forces and its acting line of action of forces distances. So what is the significance of this Z and what is the significance of this R value and all that we'll see in the next class. So for now we'll conclude this class here, and before concluding we will just revise what all we have just discussed in this tutorial. So in this class you have learnt about the definition of a dam. So if you remind yourself, a dam is a structure constructed which is made up of masonry or concrete, which is constructed across a river or a stream. And what are the main purposes of this dam? So it is constructed for various purposes. So most commonly those are for drinking purpose or for irrigation purpose, and also for in some cases for power generation purposes. It doesn't mean a dam is only intended for one particular purpose. It can be multi-purpose, I mean to say. So most of the dams, 80% of the dams will be for drinking and irrigation purposes only. And if the volume of the dam is huge, there we can go for hydroelectricity also, I mean to say, for power generations as well. So that is the basic definition of a dam and the basic uses. And next is various forces acting on a dam. So what are the various forces which we have seen till now? First one is W, which is self-weight, self-weight of a dam. The second one is horizontal force due to water pressure. This is water force, right? And the third one, because of these two, we'll get a resultant force, right? So these three are the most common forces which will be acting on the dam. There are some other forces also, like wave pressure and wind forces and various other things, but most common things which are used in analyzing a dam structure are only these three, right? And the next part we have seen is calculation of these particular forces. We have calculated W value, and we have measured the distance of line of action of W from vertical face of the dam, and in the same manner we have calculated horizontal water pressure by drawing the water pressure diagram, which was a part of our hydraulic subject. And also we have calculated its line of action of force distance from the bottom of face of the dam. And after that, because of these two forces, I mean to say the effect of these two forces we have calculated, that is resultant force. So as W and P are perpendicular to each other, the resultant will be at, at an angle of 45 degrees to these two forces.